Okay, so let's see a few things about the perturbation theory. So far we've kind of argued that we could get pretty far without doing perturbation theory. So we got here without doing perturbation theory. What if we actually now want to calculate these series, do the renormalization group evolution? How's that going to work? And it's actually, in some ways, it's a combination of the two examples that we treated. We did an example where we had a Wilson coefficient that was just running multiplicatively, and we did another example where we had a function for deep and elastic scattering that had an integral. And we're going to have both of those situations in this case. So let me tell you how it works. So to get the hard function, you would do some matching. And the matching is actually for what people call the quark form factor. So if you wonder why people care about the quark form factor is basically the h in our formula. Not exactly, but closely related to the h in our formula. So you would do some one-loop matching by taking QCD graphs and subtracting the SCT graphs in exactly the kind of way we were already doing for examples that we treated before. So those are linear gluons. This is an ultra-soft gluon. And there's some wave function graphs that you can consider. We form the difference. And at one loop, we check that all the IR divergences between this and this cancel. And then we get the Wilson coefficient. So this is very, very analogous to the example that we did when we were doing a heavy to light current. And you see here that this thing which depends on mu, it's mu over q, right? And that's what I was saying, that the Wilson coefficient or the hard function should be the log should be minimized for mu of order q. And we see that by doing the calculation. H is simply square of this thing. So there's imaginary parts from these negative logarithms. These are minus q squared minus I0. But when I take the mod square, this thing is real. What about the jet function? Well, if you go back to what the formula for the jet function was, the jet function is basically two fields, like spit out a quark and absorb a quark, but it's a vacuum matrix element, so the quarks are just contracted. So you're basically calculating graphs like this, or really actually the imaginary parts of graphs like this, because the way I drew it, you were summing over final states, so it would be the imaginary part. So we could just calculate the graphs without putting a cut in and take the imaginary part, and that would actually be giving us the jet function. So the jet function comes from some Feynman diagrams that look like this. And then there's one more. Looks like that. Okay, so at one loop, we have those three Feynman diagrams. And then we have the tree level guy. We take the imaginary part. We get the jet function. At lowest order, it gives a delta function, just a cut propagator. And then at one loop, you get a delta function, and you also get plus functions. We'll not worry so much about what the numbers are, and just tell you what the result looks like. Looks like that. There's three different types of terms that one could get. They all kind of have a power counting that makes them go like 1 over s. And that you know ahead of time. If you power count the operator here, it should scale like 1 over s. These are the different kind of structures that you can get at one loop that scale like 1 over s. And this is kind of a symptom of there being 1 over epsilon squared divergences. And this guy here, I'm writing the renormalized result. So we're taking care of the renormalization. So just like in our example, I mean, it's the same diagram, really. That this diagram, was familiar because this diagram was showing up in beta s gamma, right? So we saw it had 1 over epsilon squared poles. Here, the 1 over epsilon squared poles lead to this. And really, you can actually think of that very closely related to what we did, because we were finding logs of mu squared over p squared. But here, p squared is a physical thing. It's the s, the invariant mass that we pump into the operator. S is kind of what we put in through the moment. We put in a momentum, if you like, q, where I shouldn't call it q. T, mu, where s is t squared, right? And so before, we were having logs of p squared, which were an IR regulator, but in this calculation for this jet function, it's actually a physical thing. And it's giving the momentum dependence of the jet function that it's the right thing to stick into the factorization theorem. And then there's the soft function, where if it's perturbative, we can calculate it. And you can draw these kind of in some notation for the Wilson lines. So here's our Wilson lines in different directions. And then there's matrix element squared. And again, you can sort of think of these as kind of cut graphs like that, if you like. And if we look at the soft function, it kind of has a similar structure to the jet function, but now with the, so again, it's got a delta function and then plus functions. Whoops. And it turns out there's no single plus function, but there is a plus function with a logarithm in this case. And then same for L minus, same structure. It's just a product, if you like. And the reason that happens is if you only have one gluon, it's either in hemisphere A or hemisphere B. It can't be in both. So the alpha S corrections are either a function of L plus or a function of L minus. And that's why it has a kind of very simple structure at one loop. So that gives you an idea kind of what these perturbative functions look like. C, if you talk about renormalization, C renormalizes multiplicatively. And so the renormalization group equation for C is just like the one we had before for beta S gamma. There's no integrals. And that again came about from the kinematics fixing the variables. But the jet function and the soft function have convolutions. In this case, well, they depend on this non-trivial momentum, and it's you can see in the factorization theorem that it's convoluting between two different sectors, and that kind of is generically a hint that you're going to get out a formula like this, which is like the PDF, but now it's a different formula. We have this kind of anomalous dimension for the jet function. So we could go through that by, I was not writing down for you what the 1 over epsilons look like, right? But we could go through the renormalization and find these results. And actually, in this jet function case, we even know more. the general structure of this anomalous dimension is actually simpler than the parton distribution case. And it's the following. There's two types of terms that can show up. So the general structure of the anomalous dimension is that there's a single plus function in it or a delta function. And this single plus function is the analog in the jet function of the single logarithm that was showing up. Remember that when we decompose this guy, there could be a log mu over q term or a 1 term with no log of mu over q. This is like an analog of a log, this plus function. If you integrate over s, then it's like ds over s, which is like a log. So this is a log. And integrating delta of s is like 1. Right? So the analog statement that there was two possibilities there. In this case, there's an analog of that, and there's two possibilities here. And what perturbation theory is doing is actually just computing the coefficients of these two different structures. Okay? And we're out of time. So I'll say a few more words about how you would solve, for example, an equation like this one. Next time, I'll tell you how to solve it, and then we'll basically be done with our example. We'll put things back together and write down a factorization theorem that includes the resummation. And then we'll go on to another example. Moving on, the next example we'll treat after this one is SCT2, where we'll be dealing with energetic hadrons and some other types of examples besides jets.